All right, we are now ready to start Lab 5, which is scanning tunneling microscopy. This is a relatively simple lab. We won't be really doing much beyond running an instrument. Probably won't even be running the instrument that much because, well, we'll see. We'll see how well we can get images in the new lab, but in my experimenting so far, I haven't been able to get good images, so we'll see. What I'm going to talk about today is the background, mostly, for this experiment. So the STM is one of three microscopes, three types of microscopes that are able to resolve individual atoms. The three microscopes that can do that are the transmission electron microscope, a TEM, the field ion microscope, FIM. That's TEM, probably most people have heard of. The FIM, probably I wouldn't be surprised if nobody had heard of that. It's a really rare kind of microscope, but it can see atoms. And the third one is the scanning tunneling microscope, STM, which is what we're going to be working with this week. As I say here, of these three, only the STM works on a broad range of samples. That is, well, it does have some limitations. Not every sample can be seen by an STM, but it's a pretty broad range within those limitations. And is relatively cheap and simple and small. That's what makes it possible for us to use it for this week's experiment. If it were a big, huge, $1,000,000 piece of equipment like a TEM, then we probably wouldn't be allowed to use it for a lab like this. All right, so before we talk about the STM, let's look at the other two microscopes and see what they can do, because part of this semester's program is to get everybody to know some stuff about the techniques that are out there. So TEM, transmission electron microscopy, is essentially the analog of a light microscope, but using electrons instead of photons. So there's a source for the electrons. That's basically a sharp pointed tip with a high voltage, something like 10,000 volts applied to that tip. That voltage actually sucks electrons out of the metal tip and accelerates them towards the sample. Whatever that happens to be, the electrons then hit the sample and they're deflected or diffracted. And then there's some focusing electronics that come after that, so the electrons are refocused, and the focusing results in spots wherever there is an atom or some other thing that blocks the electrons up in the sample, and a light spot, a light background, wherever the electrons got through without being deflected. So that's exactly what a light microscope does. And the only difference, or the main practical difference between a light microscope and an electron microscope is that electrons have a de Broglie wavelength, right? If they have the de Broglie wavelength is Planck's constant divided by mv divided by the momentum of the electron, which means that if you get the electron going fast enough, Planck's constant is a very small number, of course, then the wavelength is very small, and that means that the wavelength of the electrons impinging on the sample is extremely small, much smaller than the wavelength, than the electrons, than the atoms themselves. And that means that unlike light microscopes, which are limited by the wavelength of the light that you're using, by diffraction limited, so to speak, electron microscopes are not diffraction limited. Their resolution is limited by other kinds of factors. But there are two chief drawbacks to the TEM. The one is that you've got to get the electrons through the sample, which means it can't be very thick. A few atomic layers thick is about all it can be. Maybe 10 or 20 atomic layers thick is about all it can be, before things get so confused by the time the electrons get through the sample that you can't see anything anymore. And so you've got to have a thin sample. That means a thin film, or a thin edge of a crystalline wedge. So sometimes you can fracture crystals in such a way that there's a thin edge that you can shine electrons through. Or some other sort of sample like that. A typical TEM sample, in fact, is a very thin film of carbon atoms with something deposited on the carbon atoms, and then you shine electrons through that. So basically the sample itself is suspended on a very, very thin film, a few atoms thick, and that's how you are able to see things. The other drawback to the TEM is that it is a huge multi-million-dollar instrument with an ultra-high vacuum, or at least a very high vacuum, set up in the middle of it. And therefore you can't, you can't have a TEM in your own lab probably. You have to have a TEM or an electron microscope facility available to you, and you get charged per hour for using the thing. So it's a rather complicated and difficult and expensive item of equipment to use. The field ion microscope is unusual. Like I say, I imagine most people or everybody here has not heard of a field ion microscope. It works in the following way. You have an ultra-high vacuum chamber, a really high vacuum chamber, and you introduce into that chamber a low pressure of some inert gas like argon. And also in that chamber is a metallic tip, and you apply a voltage between the tip and some detector screen. And what that means is that the voltage pulls the electrons back away from the tip. So basically this end is positive. That means the electrons get pulled away. And that leaves a very high positive charge right at the end of the tip. So there's a positive charge on the end of the tip here. And because the tip is very sharp and very small, that makes a huge electric field right in the neighborhood of the tip. That electric field is so high that it's capable of pulling electrons off of the argon atoms. And that leaves the argon atoms positively charged momentarily. And now because those positively charged argon ions are near a positively charged tip, there's a repulsion and the argon atoms are accelerated away. Because the pressure is so low in the chamber, the argon atoms are unlikely to encounter anything else before they reach the detector screen. So the argon atoms basically become ballistic little BBs that get radiated away from the tip and arrive at the detector screen. Now, that would give you nothing but an image of sort of a big blob, a big useless image, except for the fact that if you adjust the voltage right, the probability of an argon atom being ionized, having its electron removed, is much higher if the argon atom encounters a point on the tip that has an atom there, rather than some point in between the two atoms. So the rate of ionization is much higher at the atoms than it is between the atoms. And that means that on the detector screen over here, you see a stream of argon ions arriving that leave a high-intensity spot where the atoms, corresponding to where the atoms are on the tip, and a low-intensity area in between the atoms. And so you get an atom-by-atom image of everywhere on the tip. And so the field ion microscope can see atoms, and now you can start decorating this tip with all kinds of other things, and you can see whatever those decorations are as well. And so it's more than just seeing the atoms that are actually part of the tip. You can see atoms that are dosed onto the tip as well. And that's great. You can see atoms. You can even see atoms moving in real time. It's kind of fun to watch some of these images, especially with the better FIM people. But it's also a big instrument, a big, well, I don't know if it's $1 million instrument. Probably it is now these days, a multi-million-dollar instrument also. It also uses an ultra-high vacuum chamber. It's a big, complicated thing and hard to use. And that means there aren't very many field ion microscopes in the world. They are much, much less common than either STMs or TEMs. And so I bring this field ion microscope up so that you know about it in the future. If you ever have a problem for which a field ion microscope would be useful, then you can start inquiring about gaining use to a field ion microscope, but they are very rare. That brings us to the third type of microscope, the STM. And that's the one we're going to be using today, of course, or this week, of course. The STM is a so-called probe microscope. It's one of a whole family of microscopes that basically take a very sharp tip of some kind or another and scan it over a surface and follow the surface at some distance, some small distance from the surface, and by recording the ups and downs of the tip as it's moving over the surface, creates an image of the surface. It raster scans over the surface and creates an image that way. So the common types of probe microscopes are the STM itself, and then another one called an atomic force microscope. That's probably actually the most common kind, and maybe in the future we'll, our instrument can do both AFM, so this is AFM or STM, and so maybe in the future we'll do atomic force microscopy someday, but for the moment we're working on STM. And the reason for working on STM is that it has higher resolution than AFM does. AFM typically has resolution of a few nanometers. STM, on the other hand, can oftentimes see individual atoms, resolution on the angstrom scale. And then there's a whole bunch of other kinds of microscopes. Basically, anytime you can make a probe tip that can somehow sense the presence of the sample surface, you can use that sensitive interaction to create a probe microscope of one kind or another. There's probably a couple dozen different kinds of probe microscopes out there, but STM and AFM are the two most common kind. I won't talk more about AFM for now. If people are interested, I can talk about it in detail. Actually, in my research career, I've done a whole lot more AFM than STM, and so if you want me to talk about that, I will. But let's talk about STM since that's our instrument for today, for this week. So here's how an STM is built. You have a metal tip or a conductive tip of some kind with a very sharp point or tip. There's a sample which also has to be conductive. So the primary limitation for the STM is that the sample has to be a conductor. It doesn't work, for example, if you're trying to take an image of a protein, because the proteins are good insulators. They're the opposite of conductors. People tried to take images, for example, of DNA for a long time. Just doesn't work with STM. But AFM it works with, and so if we wanted to talk about AFM, we could talk about imaging biological samples. For this semester, we're going to talk about imaging conductive samples, specifically elemental carbon in the form of graphite, which is a good conductor. So the sample is then sitting on top of something called a piezoelectric tube positioner. And let me say something about that. We'll look at that when we actually do the experiment this week. But the piezoelectric tube is a piece of ceramic material that's shaped like a tube, a hollow tube. And on the outside of the tube are some electrodes, some metal coating that's been plated onto that, onto the outside, and then also onto the inside, and you apply a voltage between those metal coatings. Lots of voltages in these high-resolution microscopes. And as a result of that voltage, the thing that's unique about these materials is that they're piezoelectric, which means that if you squeeze the material, they generate a voltage, but it also means in reverse, if you apply a voltage, then they expand or contract by a very small amount. And so if you apply a voltage between the inner and outer electrodes on this tube, then this tube can stretch a little bit. It doesn't stretch very much. It stretches by a tiny amount that you can't even have any chance of seeing with your eye, but it does stretch a little bit, and that's exactly what you want. That means you can control the height of this sample by applying voltages from the computer. It turns out that by clever arrangement of the electrodes, there's more than one electrode on the outer surface here, you can also make this piezo bend a little bit, and that means that you can cause the sample to slide back and forth in the lateral direction also in either X and Y. And that means that a single tube piezo can cause the sample to move a little bit in both the X and the Y and the Z directions. So that's how it works. You have this tip that comes close to the sample. You've got this piezoelectric positioner underneath the sample. And you apply a small voltage, usually less than a volt, maybe about 1/10 of a volt or so, between the tip and the sample. And then you carefully bring that tip down towards the sample until it gets just a few angstroms away from the sample. And then what happens is, before you even touch, electrons start to be pulled by tunneling between the tip and the sample. Basically, the atoms in the tip have a certain orbital, quantum orbital, and the atoms in the sample also have a certain quantum orbital or quantum wave function. And when those wave functions start to overlap a little bit, the probability of an electron hopping from the sample to the tip, or vice versa, they can go either way, starts to get high, and then you start getting a current of electrons flowing between the sample and the tip. And it turns out that that current is extremely sensitive to how close the tip is to the sample. So under usual conditions, the current that you see flowing between the tip and the sample, current's a macroscopically measurable quantity after all, so your instrument is measuring the size of this current, and it turns out that that current depends on some constant, some initial current, times the distance between the sample and the tip, x, divided by, in units of angstroms. In other words, if I move this tip let's suppose I'm at 10 angstroms to start with, and I move it down to 9 angstroms, so it moves down closer by only 1 angstrom. According to this formula, that makes the current go up by a factor of 10. Likewise, if I move away by an angstrom to 11 angstroms, that makes the current go down by a factor of 10. So I get a great big change in the current for very small changes in the tip sample distance. And that means I can tell exactly how far my tip is from the sample as I scan the tip over the sample. It's extremely sensitive to the size of the tip sample gap. All right, what that means then is that if I scan the tip over the surface, whenever there's a bump on the surface like these blue areas, then the current goes way up as the tip starts to encounter that bump. There's a feedback circuit that causes the piezo positioner to retract the sample a little bit so as to avoid a tip crash, to keep the tip away from the sample. And you record the voltages that are needed to prevent the tip from crashing. And that amounts to recording the bumps and wiggles and features on the sample. It turns out that because everything is so sensitive, because the tunneling current is so sensitive, if the bumps on your sample are due to the individual atoms of the sample itself, that's enough to cause a measurable current change from point to point on the sample. And so you can see the high current areas will be where the atoms are, the low current areas will be between the atoms, and so you can see the atoms on the sample. All right, that's how the instrument works. A little bit about how the tunneling process actually happens. The tunneling process works like this. I have this so-called bias voltage between the tip and the sample. That bias voltage represents a difference in energy for electrons between the tip and the sample. And the way it's set up right now, electrons would be at a somewhat different voltage or somewhat different energy when they're in the sample than when they are in the tip. But when the electrons are in the sample, they're at lower energy, or when the electrons are in the tip, they're at lower energy than they are when they're in between. So if the electron starts here and goes towards the tip, then, let me draw it more like it would actually be. It'll go to the tip first. Then its energy starts sort of medium, then it gets very high because we're in vacuum, and then it goes back down to the lowest energy possible when it's in the tip. The electrons are basically being, statistically at least, sucked from the sample toward the tip. Now, you can reverse the voltage so that it's going the other way, and then you can push electrons from the tip into the sample. It doesn't matter which way the voltage goes, but you can, and you can adjust the value of the voltage. We'll see all these things as we're doing the experiment. Now, classically, let's see what I want to say here. Yeah, classically, well, let me go back up here. The fact that the energy of the electrons is high when it's in the barrier means that if an electron comes in with typical energy for this sample, it doesn't have enough energy to, it will get reflected, it would bounce off the surface of the sample if the electrons were classical. And the same is true for the tip. If an electron comes in, doesn't have enough energy to achieve the barrier energy, then it would just bounce off and go back in. So the electrons, and that happens to most of the electrons. In fact, the electrons are coming in, bouncing off the surfaces of the tip and the sample all the time. And if the gap between the tip and the sample is too big, then that's all that ever happens. But when the gap starts to get small, so typically around 10 angstroms is small enough. That's small enough so that the wave functions in the tip and the wave functions in the sample start to overlap a little bit. Then it becomes possible, and down here is the picture, for the electrons to tunnel into the barrier region. There's a non-zero probability of finding the electron in the barrier region, even though it doesn't have enough energy to get into the barrier region classically. And what that means is that there's a non-zero probability of the electron crossing from the tip to the sample or from the sample to the tip, vice versa. Working out the quantum mechanics of this situation, and the quantum mechanics aren't too complicated, but it's more difficulty than we want to go through here. If you work out the quantum mechanics of that situation, then that's where this formula comes from. It's, like I say, it's not beyond the level of this class to work out that formula. And if people are interested, I'm happy to do that. But it would take, well, probably an hour or two to do that. It is a little bit complicated. It isn't difficult, but it does involve some math. And anyway, you can derive this formula that tells how the current varies with the size of the tip sample gap relatively easily. Yeah, I think everybody who's had a semester of P-Chem anyway, a semester of 311 anyway, has enough background to actually derive that formula. I guess I'm kind of challenging people to see if you can derive it. You can find these derivations on the internet easily if you Google them. If you Google scanning tunneling microscopy or electron tunneling, you can get some help on that if you're interested enough. All right, this is a discussion of how the electrons move inside conductors and talks about conduction bands and valence bands and Fermi levels and all those kinds of things. But I think I'll leave that for people to read. I won't lecture on that. So let me just skip over that and come finally to a discussion of the actual sample that we're going to be looking at for this week. And that's graphite, which is, of course, elemental. It's the most stable form of elemental carbon at room temperature and pressure. So it is elemental carbon in its most stable state. This is the type of carbon that gets a free energy value of 0 or a delta H value of 0 on all those thermodynamic tables that you've seen since you were in freshman chemistry. But it's a particularly nice form of graphite. Mostly graphite is ugly stuff whose crystalline structure is all busted up and destroyed. The type of graphite that we're going to be talking about is highly oriented pyrolytic graphite, or HOPG. You can't get this out of a pencil. You get this stuff from a supply house of some sort. It's quite expensive, hundreds of dollars for a little teeny 1 centimeter chip like we're going to be using for this experiment. And it's basically, I mean, what this really amounts to is nearly perfectly crystalline graphite. So nearly perfectly crystalline graphite is a series of layers. The layers are called graphene layers, and they're just stacked on top of each other each layer with a distance of 3.34 angstroms from each other. We'll see that distance in the STM most likely, because the graphite surfaces that we're going to be looking at aren't perfect. Some of these surfaces terminate, and then the STM will see that step on the step edge on the graphite surface, and we'll be able to measure this interlayer spacing. We'll be able to tell whether we're seeing one interlayer spacing or two interlayer spacings, whether the interlayer spacings are staggered or whether they've both been cleaved at the same point, and so on. We'll be able to see all those kinds of things. Each of the graphene layers themselves is a honeycomb lattice of fused hexagonal rings, fused benzene rings, really. So it looks something like this. You can think of it, yes, as a bunch of fused benzenes, both in the sense that they're flat hexagons and in the sense that the electrons in the above the graphene layer are delocalized over the whole array, the whole huge, essentially infinite graphene layer. In other words, all these hexagons have p orbitals above them, which have one electron each, and all those p orbitals are conjugated with each other. And if it were benzene, those conjugated electrons would form an orbital that's a little ring above the benzene ring. But since all the benzene rings are fused, they form a giant pi system that extends over the entire graphene layer, extends over macroscopic distances. It's one big orbital that's macroscopic in size. And the electrons can move essentially without friction, or with very little friction anyway, in that whole giant orbital layer. Talking about what that means for the quantum mechanics of something like, well, of any conductor, but especially something like benzene, that's what this section we skipped is talking about, actually. It's talking about conduction bands and valence bands and infinite delocalized orbitals. All metals have infinite delocalized orbitals. The graphene ones are particularly kind of fun, but all metals have them. And so that's the part we skipped. If you're interested in that, go back and look at it. The atoms, the carbon atoms themselves within these graphene layers are separated by, or have a bond length of 1.42 angstroms. I'm giving you all these distances, 3.34 angstroms and 1.42 angstroms, because those are measurable by the STM. We're going to see how well we can measure those things from the images we collect. And that's the actual distance between the carbon atoms. And in principle, the STM could see the individual carbon atoms, but what we'll see in our images, we probably won't be able to see every single carbon atom. It's very unusual that you can see every single carbon atom, and we'll see why. The reason is this. Here's one graphene layer. Here's another graphene layer. And now I'm going to take this graphene layer, layer A, and stack it on layer B. How do they stack? Do they stack with all the atoms lined up with each other? No, they stack with half the atoms sitting in the hollows of the lower layer, but the other half of the atoms, yes, sitting on top of other carbon atoms in the layer below. That's just the best way that you can stack these two on top of each other so as to maximize their interaction between each other, their favorable van der Waals interaction between each other. And what that means is that in this upper layer, in layer A here, which is all the STM sees, right? The STM can't see the lower layers. So the only thing the STM sees, well, the STM sees two different kinds of atoms. It sees atoms that have another atom below them, and it also sees atoms that don't have another atom below them, that have a hollow spot below them. And it turns out that for quantum mechanical reasons, what the STM mostly sees are just the atoms that have another atom below them. And that means that there's a very strong tendency in almost all STM images of graphite. You see only half the atoms. You don't see these hollow site atoms on layer A. Which means that what you see is an image that looks something like this. You see an image that looks like a hexagonal arrangement of atoms, not a honeycomb layer, right? A honeycomb layer up here looks like this. It doesn't have any dots in the center sites. You see these hexagons with no dot in the middle. That's not what you see in a typical STM image. You see a hexagonal lattice with all the dots present. But what that means is that the actual benzene rings, you're only seeing half the atoms, the red atoms in this picture. The other half are basically invisible. And that means that the effective spacing between the high points in the image is 2.46 angstroms. It's not 1.42 angstroms. All right. So understanding what you're seeing in the STM requires a little bit of this crystallography that we're going through now. All right, so that's the sample we're going to look at. That's the graphite sample that we're going to look at. The reason we're looking at graphite, we'll see some of the more of the reasons down below. But the basic reason is that it's really easy to get atomic resolution images on graphite. With a little bit of work, you can usually get something that at least reflects the atomic scale structure of the graphite. There are very few other samples where things are that easy. We can talk about other kinds of samples that you can image with the STM and maybe get atomic resolution, but graphite is by far the easiest one usually. However, there are issues. We will not get this image that we're seeing here that's showing half the atoms. That's a really good one. Last year, we got one that was almost this good. We were very lucky, I have to say. I don't know if we'll get this lucky this year or not. We'll see what we can get, but it's rare that you get an image this good. And the reasons why you rarely get images that good. I mean, let's put it this way. If we had a couple of days to fool around with the STM, we would get an image this good. With enough, effort and trying and trial and error, you'll eventually, without too much terrible work, if you're a graduate student who's got days to put into getting these kinds of images because they're important for some research objective, you would get an image this good pretty quickly, probably within the first day, probably within the first half day even, on a sample of graphite. Other samples are harder, but still, within a few days of effort, you can usually get something like atomic resolution. But it does take that much time to get the odds up that you'll get. I mean, you can get lucky too, but to get the odds up high enough that we're likely to see an atomic resolution image, probably we're not going to be able to do that within the time of one single period. So it's unlikely that we'll get images this good during our short session of one afternoon. And here are some of the reasons why. The primary reasons are drift, bad tips, and surface contamination. Bad tips, I imagine you can imagine what that means. It means a tip that's not atomically sharp, not sharp enough to even get this kind of resolution. Surface contamination means some kind of garbage on the tip, on the surface. It turns out that's less of a problem than you might imagine. We'll see why. And drift, probably nobody knows what that means, but we'll talk about it down below. All right, here's what the tip actually looks like. I've drawn these idealized tips that look like this up to now. But if you look on the microscopic scale, actually, if you can look at STM tips with a TEM and get atomic resolution images of the tip, because it is a thin sample, and what you see is stuff that looks like this. They look ugly. There's two kinds of tips that are most common. One is a tungsten tip that's etched chemically, and I can tell people how you do that if you're interested. The other, but that takes some work, and not only that, the tungsten oxidizes in air, so there's always an oxide layer you have to worry about, and that can cause troubles. The other kind of tip is that you use platinum iridium wire. Why platinum iridium? Well, because it's a conductor, for one thing, but platinum also doesn't oxidize in air, which means once you've got it clean, once you've got the oxide layers off, it doesn't reoxidize, at least not on any kind of reasonable time scale. So for a few days at least, and probably longer, the tip stays clean. Well, it doesn't get this insulating oxide layer on it anyway. And the reason for the iridium in there, the iridium's a really rare and expensive chemical or element. Why iridium in there? Well, it makes the wire stiff enough to use. Platinum's too soft to really use, so you got to put something in there to stiffen it. And so platinum iridium wire is sort of the standard thing to make a tip out of. How do you make the tip? Well, you take a pair of scissors and you just clip it. And that creates the ugliest, scraggly thing you can imagine, and you just pray and hope that at the very tip end of the tip, one of those little tipettes is a few angstroms lower than the other, right? Because the tunneling current is so sensitive to the tip sample gap, all it takes is that one atom is just a few angstroms lower or closer to the sample than all the competing atoms. Those competing atoms will contribute a little bit to the current, but it'll be 10 times less, or maybe even 100 times less. And so that one single lowest atom can dominate the tunneling current, and that's the virtue of the STM. It means that even just by chance, you're pretty likely to get a tip that's effectively atomically sharp. All right. The other reason that graphite is so great is that because it's a layered material, you can take a piece of Scotch tape, stick it down on the graphite, pull the Scotch tape up, and it will pull up, it will tear off the top few layers of graphite. And that means that whatever crap was on the surface of the graphite to start with is now all torn off. You've got a completely new layer that's just recently been unburied. You've what's called cleaved the crystal, and that leaves behind, a nice clean surface with maybe some step defects or other kinds of defects. And you can see all that. You can see the atoms when you're looking in between the defects, and you can see the defects when you widen out the scan area. Now, if you leave your nice clean surface exposed to air for any length of time, for really about 20 minutes is my experience, stuff from the air starts accumulating on the surface. And so the question is 20 minutes enough time to see a good image from the STM? The answer is no. It takes longer than that for various reasons. We'll talk about those when we actually do the experiment. And that means that what you're actually imaging isn't, a clean sample. It's a sample that's been cleaned of its worst stuff, but within a few minutes or maybe an hour, maybe a few hours, it started to accumulate crap. And that means that what you're really doing with the STM when you're imaging in air, when you're not imaging in ultra-high vacuum or some other really controlled environment, is the tip, all this crap, all this grease that deposits out on the surface is insulating, right? So the tip doesn't see it. It just plows its way right through those grease layers. And then it starts scanning, through those grease layers. And unless the grease layers are particularly wet, water is bad because water can participate in redox reactions, which means it can behave as if it's conductive, and which means it generates noise and other kinds of garbage. So you want a nice dry environment. But apart from that, any organic material that comes from your body or from whatever else may be around and ends up accumulating on the surface, that just doesn't have too much effect. You can still see the atoms underneath. All right. So those are the difficulties. This is the contamination or surface contamination issue. This is the bad tip issue. I mean, fairly often it does happen that you just don't get a sharp enough tip, or that it's gummed up or goobered up for some other reason. Tips crash onto the surface and so on. Anyway, bad tip is one possibility. Surface contamination is the other. But the thing we're going to be mostly fighting probably when we actually do our experiment is drift. So remember that the STM looks like this. It's got a sharp tip. That tip is mounted on some kind of holder, and then there's a sample that's also mounted on some kind of holder, and then there's some kind of mechanical armature or connection that connects these two. We'll look at what that is. But that means that if there's small thermal differences between here and here, these materials are all expanding and contracting slowly as temperature changes. And that means that this sample is moving a little bit from thermal expansions and contractions, and it's also, the distance is also drifting, the distance between the tip and the sample is also drifting a little bit, and that's thermal drift. And that means that as you're scanning, it takes quite a while to get an STM image usually. It can take about 30 seconds or several minutes even to get an STM image, and all that time your sample is drifting because of thermal changes. And that means that very often, here's the ideal image, here's what you actually get in effect because the sample was shifting as you were scanning, and you got to correct for that. We won't do any of that kind of stuff. That's too complicated for our current purposes. Or you can try to control the temperature, which people do. That's probably the better thing to do. But we'll be fighting with this thermal drift when we take our images because we just don't have that type of controlled environment. All right. Here's what the STM looks like. We'll see it when we actually do the experiments. There's an STM head. The tip is mounted in that head. There's a piezoelectric scanner, which looks like a cylinder of metal, but it's got a piezoelectric element inside of it. And then there's a base that everything is sitting on. The electronics are all on that base. The electronics are connected to a computer, which provides the voltages that cause the piezoelectric scanner to wag and to stretch or contract. And then there's also detector electronics up in this head that are measuring the tunneling current that's flowing between the tip and the sample at all points. And the whole thing's pretty small. You can fit this into a good-sized coffee can. And in fact, the truth is that STMs are not terribly difficult machines to build. You could build your own STM in your own garage. People did this in the early days with, a few days of effort. You can order all the parts now online. You can program your own computer to create software that'll run your thing. You got to order a few high voltage amplifiers and the like, but and it probably costs you a few $100s by the time you're done. But you can build your own atomic resolution, high resolution scanning tunneling microscope on your own, in your garage, at your kitchen table, wherever you want, with not too much effort if you know what you're doing. All right. Yeah, there were stories that went around in the early days about graduate students assembling new STMs. These are research people, of course, whose research was STM, so they really knew what they were doing. But they would assemble a new STM while watching a football game, watching the Super Bowl back in the old days. And so it's not hard to do. Once you've got everything set up to do, it's really not that difficult. The instruments this is just sort of almost the opposite of a TEM, which is a giant monster of an instrument. STMs are simple, and you can make them even simpler and smaller than the one we're going to use. All right. I think we'll leave the rest of this for the actual time. We'll be adjusting software values. We'll be adjusting the value of the tunneling current, the speed at which the tip scans over the surface, the size of the scan region. There's a feedback circuit, and it has certain settings to make it either more sensitive or less sensitive. We'll be adjusting and optimizing those feedback settings. And then there's different kinds of scanning contrast types. You can measure the height at which the tip is over the surface, or you can measure differences in current as you're scanning over the surface. Both of those are viable ways of getting a good image, and so on. All right, I think that's enough for today, and we'll talk more on Tuesday.